We now want to take a look at how we can solve systems of linear equations by hand. They can be solved on the calculator, but there are some problems that aren't easily solved on the calculator because of fractional answers, for example. So we want to look at how they can be worked by hand. Now, you've looked at linear equations before, even in two variables. If I had a linear equation like 3x plus 2y equaling 12, and you were asked to come up with a solution to this linear equation, if it was just a single equation and not a system, then what you could do is to pick, say, an x value, plug it in. Now, once that number is in place, once you've made that substitution, what you are left with is an equation with only one variable in it, which is something we already know how to solve. You can go through using your addition property and your multiplication property of equality and solve for the other variable without a whole lot of difficulty. So, given a value to put in for the x variable in this case, I was able to find the y variable, the y value, very easily. And that is the principle that this substitution technique is based upon. If you can make a substitution and make the equation go from two variables to having only one variable in it, then you can solve in an outright fashion. Let's look at an example of a equation that's going to be given to you in a fashion where it's fairly easy to do that. If your two equations were x equals 3 and x plus y plus 5 equals 0, then you could look at the first equation and say, well, I already know what x is. I pretty much have half of my answer. You could then come down, remove the x variable from the other equation, put in its place what you know it to be equal to, combine some like terms, the 5 and the 3 become an 8, use your addition property, and you've got a solution. And again, this is pretty much what we're going to be doing as we use our substitution technique. But an actual numerical value for the variable is not always what's going to be given. Let's look at another example. Say we had x plus 2y equaling 6, and we have a 2x minus 3y equaling 5. We're going to take the first equation and we're going to solve for x. Now, why did we choose that? Well, you notice if we choose the x in the second equation or either one of the y's, because they have coefficients of 2 and 3, we're going to end up with fractions. So solving for this x is our best option, because when I solve for it, by subtracting the 2y over, I've got no fractions. It's a very easy thing to solve for. So I'm going to come down and use the substitution technique just like I did before. But with this technique, the idea is you're going to try and get this equation from two variables down to only one by substituting in what you know x to be equal to. But this time, we don't have a numerical value for x. We have an expression here that tells us what x is. But that's good enough. I can put that in, and I have, once again, gone from a system with two equations and two variables down to only one equation and only one variable, just like I did over here when I made this substitution. So I can distribute the 2. 2 times 6 is a 12, minus 2 times 2 would be a minus 4y, and the minus 3y that was already there. Combine like terms, subtract off the 12, divide by negative 7, and I know what y is. And again, remember, with these systems of equations, a solution is an ordered pair, as in two values, an x and a y. So with a substitution problem, you typically have to substitute. Normally, you have to substitute at least twice. I can take this value that I know for y and put it in for y in the first equation, put it in for y in the second equation, or put it in the y for the one that I made. And I think that's what I'll do. And you've got a complete solution now. Alright, so with your substitution technique, you're actually going to end up, in most examples, substituting at least twice. Now let's go to a new example. We're going to now look at a x plus y equaling -2 and an x minus y equaling 0. Now I want to look at this one because this is an example of where you got multiple different options as to which variable you might want to solve for. Every single variable here has a coefficient of 1, so they would all be easy to solve for. I'll just take the first one, and that's going to give me x plus y equal -2 will give me, when I subtract off the y, x equaling -2 minus y. And like before, I come to the other equation. You always have to make use of the other equation. You can't use the same one twice. And I substitute in exactly what I found x to be equal to. Drop the parentheses this time because there really is nothing to distribute. Combine like terms. Add 2 to both sides. Get -2y equaling 2. When I divide, I get y equal -1. And again, I have the choice. I want to substitute it back into the y in the first equation, second equation, or the one that I created. I'll again choose to put it back exactly. We'll put it back into the one I created. And I have my x. And again, same reminder. Your solution is an ordered pair, as in an x value and the y value that goes with it. Alright, so the essence of this particular procedure is solve for the variable that is easiest to solve for, which is typically the one that has the coefficient of 1, perhaps -1. That wouldn't be hard to solve for either. Make your substitution. This will give you one equation with one variable. Solve for that one variable, and you've got half of an answer. Don't forget to plug that half of an answer back in to get the second half of your answer. Let's look at a couple examples now where something a little bit different happens. If you look at these linear equations graphically, you'll realize that it is possible to have one solution, or no solution, or infinitely many. Well, the examples we've done have shown us one solution in each case. There are other things that can happen, though. Let's look at 3x minus y equaling 14 and 6x minus 2y equaling 10. Now, which variable should we solve for? Well, I'm going to go for the y in the first equation because it has a coefficient of -1. So I'll step aside, subtract off the 3x, get -y equaling a 14 minus 3x, divide by -1, I got y equaling a -14 plus 3x. So now to make the substitution, I remove the y variable in the other equation. I put in exactly what I just found it to be equal to, and now I can distribute. -2 times -14 is a plus 28. -2 and a plus 3 is a minus 6x. When I combine terms, the 6x's cancel, and I get a 28 equal 10. Now you notice something really strange has happened here. The first thing hopefully you notice is the variable completely disappeared from the problem. And after that, what we were left with can only be called a false statement. That's simply not true. So this implies that this problem has no solution. That's what is implied by the false statement that was left after the variables were gone. And again, you have to make sure that the variables do in fact cancel out of both sides completely before you can make this type of conclusion. Now the other problem we're going to look at is going to be y equals 1/3 x minus 2 and x minus 3y equaling 6. In this particular example, the easy variable to solve for is going to be either the x in the second equation or perhaps the y in the first one, since it is in fact already solved for. So we'll go with that since it's already given to us. X minus 3 times, again opening up the parentheses, putting in exactly what it says y is equal to. Now I'm going to distribute. 3 times 1/3 is a minus x. 3 times a minus 2 is a plus 6. Here again you notice the variable completely and totally cancels out. And what we're left with can only be called a true statement. When you're left with a true statement after the variables are completely gone, that means that that particular problem has infinitely many solutions. So that's the substitution technique, and those are the answers that you can get. You can get one solution, you can get no solution, you can also end up with infinitely many solutions. Let's look at one last example to see how many solutions we come up with and see which variable it is we're going to solve for in this particular case. Let's take a look at 2x plus y equaling 11 and y minus 4x equaling -7. Now, which variable is going to be easy to solve for? Well, it would look in this example like I could solve for the y in the first equation or the second one fairly easily. Let's go for the second one. I can just come right over here and add a 4x. Get y equaling a 4x minus 7. Come up to the first equation. Put in 4x minus 7 in place of y. Combine my like terms. Add the 7. Doesn't look like I'm going to get infinitely many solutions. Doesn't look like no solution because the variable has not canceled out. This looks like a one solution case. All right, so again, I'll remind you, you have right now only half of a solution. This 3 must be put in place of x either here in the first equation, here in the second equation, or in the one you created. Again, I'm going to opt for putting it in the one that I created because it's usually set up better. And you've got a final answer. So our last example is one where we had one unique solution.